So what's on the agenda today? I presented at the DataCon 21, which was severely technical for MLOps, and discussed everything from data preparation, feature stores, data drifts, concept drifts, and logging. So if you're interested in a technical deep dive, I would highly suggest that you go and look at the recording from last year, because it covers a lot about the MLOps framework from a technical deep dive perspective. This one is, however, a hybrid. So it's got an emphasis on customer point of view. So in our case, what is a customer? In our case, the customer can be anyone who will utilize the model outputs without having to worry about the backend at all. We'll still discuss tools necessary for big compute, MLOps. So we're going to talk about data cataloging. What is that? How do you incorporate that? Databricks, what purpose is that used for? And then obviously Snowflake. And they're all kind of going to work together. That's the key point here. So we're going to think about the utility of the tool from an optimization standpoint. What do I mean by that? It means that we're not just going to think about the devs. We're not going to think about the end users. We're going to think about them together. And how can we build a system that can work together for every party involved that is going to utilize or build the system? So we're going to talk about the 3 S's. We're going to get to that in a bit, which is all about selecting the right tools, implementing them for the data science team for success. And then we're going to talk about a real-world architecture that I've been personally involved in building, and then the implementation walkthrough. So we're going to go from, how do we select that architecture and build that, and then how do we implement that and execute that? And then obviously we're going to talk about some dashboarding, the end users, and then questions. So an executive summary. In this case, what we're going to really do is the architecture selection process. How do you do that? And what is the process that you have to precisely go through to build a big compute, capability system that can churn through 500 million billion rows of data with very little friction? You're always going to have friction. I'm not going to lie to you, but how do you minimize that friction? Then implementing the architecture and then utilizing the architecture. This is kind of a key expectation from today's presentation. So question 1. How do you build a low latency end-to-end model capable of churning through billions of rows of data in milliseconds? So what you're looking at is just a teaser of a model. And essentially the key point here is, how do you actually build a system that can run the predict functions in the backend, churning through millions of rows of data and have millisecond to 1 second response system when a plethora of users are kind of hitting the servers at the same time? Question 2. How do you build simple end-to-end pipelines to communicate to all levels of SMEs? So your SMEs are here, over here, will be everyone from data engineers. We're going to talk about that. We're going to talk about the subject matter experts from the domain perspective. We're going to talk about ET teams, executive teams. We're going to talk about analysts. We're going to talk about engineers who are going to actually analyze the outputs of the model from a performance analyst standpoint. And then how do you deliver that value at the very end, keeping the sophistication from an MLOps perspective or the technical backend perspective away from the target audience? The next 5 slides is going to be a quick recap from a first principle thinking for MLOps. We're going to focus on, I wish we had time to talk about all the 6 V's, but we're going to focus on the 3 V's over here. The volume, the rate at which the data is coming in, the velocity, which is the speed at which the big data is being generated, and then the veracity, do you have trust? Now, out of the 6 V's, if you focus on these 3, MLOps really delivers. And that is because the value add in hyperscale capability really functions when you can address these 3 from an MLOps standpoint. Again, we're talking about big data, big compute, a lot of algorithms running simultaneously. How do you build something that is not going to crash? So now you think about, from a semi-technical perspective, an OLTP system, a transactional processing system, and then you're trying to move that transactional processing system into an OLAP system, which is an analytical processing system. So you're taking a capacity of high throughput, high volume, and the system has to be able to handle this without crashing, and it has to still deliver value. And the veracity part is absolutely critical, because a lot of times you will have ETL, ELT formations of data transformation, data pipelines, but no one will have actually spent the time validating the data itself in the ETL process. So that is actually a very key component, because you can manage the volume, the velocity of the data that's coming in, but if it's not validated, chances are 1 of 2 things is going to happen. Either the end user will have little understanding of what happened with the data and where the data is coming from, Or the data scientist who has obviously limited time and capacity will have build models that don't deliver value because the data is actually not validated. So let's get, just from a very high level description over here, what is MLOps? There's three components. ML, I'm not going to bore you guys to death. I think we all kind of have an understanding. ML is build models to solve problems. DevOps. Now, this is where software engineering starts creeping into data science. This is where you need to be able to understand basic software engineering principles to be able to deliver ROI on your models. So what in DevOps, very similar to DevOps, in MLOps, you have models that are versioned along with other code. So code versioning, standard software engineering practice. Model releases are built, packaged, deployed as a unit. Deployments have to be reproducible, and fallbacks are also possible. From an MLOps standpoint now looking at additional flavor that's coming in, is that you need to be able to monitor concept drift, data drift, feature stores, and model drifting. So I've talked about this in length, so I'm not going to get into the technicals, but keep that in mind, because MLOps is really software engineering on steroids, because you're taking everything that software engineering has to offer, you're taking everything that data science has to offer, and then you're merging those two and saying, okay, these are the gaps from software engineering that was needed in MLOps. And these are the gaps that we absolutely need to fill to build trust and validation for the model. So we're going to talk about those architectures. Everything that you see in this advanced MLOps lifecycle I've covered previously from a technical perspective. However, I do want to point out from the MLOps perspective, the feature stores is something that I highly, highly recommend that people are kind of missing out in their capacity. And it's extremely handy for parsing through large data and creating experimentation and deployment data sets. So in this presentation, however, we are going to build a system from a business and an engineering perspective, but at a very high level. We're not going to double click into each one of these features. We are actually going to talk more about the architecture from an APM standpoint and more from an implementation standpoint, but keeping in mind that these are all the moving parts that need to be addressed. So how do we pick that architecture that can, get us to up to 90% of all the features that are needed for all the things that you're looking at the screen? So we're talking about systems thinking in this talk. Let's talk about the elephant in the room. Today's data scientists have about murky definitions of what their job really is. In its truest form, what I believe a data scientist does is should be able to generate value through an R&D activity by leveraging data. Now, if you look at this from the top-down approach, the care level of a data scientist is diminishing, meaning that all these things that you look at in the row-by-row basis are very critical. But a data scientist, if you look at the job descriptions, is expected to fill about 90 or 80% of this. It's not reasonable, because a data scientist should just be looking at the data, utilizing the architecture, and then generating value for the organization. So we need to be able to figure out who the numerous stakeholders are, who the really good partners are who can come in and solve some of these problems for the data scientist, and then leading to prevention of burnout and obviously value generation. That's what the key point is over here with MLOps. So who are these key players? If you pay careful attention, you will see that there is a dichotomy over here, meaning the left side is focused more on the technical stuff, and the right side is focused more on the business side. And how does this two work? In an ideal MLOps, framework, you would have the left side who would solve the problems for the right side. So left brain, right brain. And it would be done by validation and trust built for the right side. Remember, the way I kind of always talk about data science is that 50% of your job is sales, because almost never is the data scientist going to be the end user of their own product. It is always that you're solving a problem for someone else who needs help with the skill set that you have to offer. But the buy-in has to come in from the customer. That can be an internal stakeholder or an external, doesn't matter. But that the business KPI versus model KPIs are two totally different things. A model metrics KPI is something that a data scientist would be very, very curious about to make sure that the model is doing what it's supposed to. But from a returns aspect, from the right side hemisphere, you actually are thinking more about P&L, all right, or accuracy from, okay, how much skin in the game can I put in on the basis of this model? So remember, the right side are putting everything on the line. The left side are really just looking at solving the problem for the right side. Now, the real question kind of comes in is how do you make the two sides deliver? So in an MLOps lifecycle, this is a very typical, general MLOps lifecycle. You'll see that I have kind of stolen these SME logos and put it on the left and the right side, on the left bottom side and the right top side. So essentially what happens is an SME, a data engineer, and data science will partner to find data that can possibly solve a problem. Now, the critical component over here, if you notice very carefully, what I'm saying is you're trying to find the data. There's two ways generally that you can solve data science. One is a hypothesis-driven approach, which is I have a theory, a hypothesis, and I want to test it, so I'm going to go looking for the data. The second one, which is Andrew Ng's philosophy, which is a data-driven AI approach, meaning that let's go look at the data and then see what problem we can solve. And that's where this is the kind of approach that we have utilized, which is let's partner the subject matter expert and the domain expert with a data engineer, because the SME knows what data to look for. The data engineer possibly knows where the data resides. And then the data scientist is kind of coming in and saying, oh, this is how all the things kind of fit together. Then what happens is once you kind of figure out where the data is, the data engineer provisions resources to build silver tables. We'll talk about that in a bit. For the data science team to scale feature stores. So essentially, the data engineer is handling, the data warehousing aspect and the data pipelining aspect. The SME is involved knowing exactly what the parameters of the input are going to be in the data science already in the model. And the data science scientist is actually utilizing and leveraging the technology stack that you've kind of built upon. So then the data scientist will experiment and validate with an SME. And then once the validation is complete through business KPIs, the MLE scales the architecture. And by scale, we mean that the data engineer will monitor concept drift and data drift. So in that case, either your features are drifting, and since the data engineer built the data pipeline, that the drift aspect, the monitoring of the data drift and the concept drift, or the target, the fundamental understanding of what you are trying to predict has also drifted. These are things that happen very often as the models kind of like run on the long term, and the data engineer will handle that. But from a performance aspect, a data scientist will partner with that. And then the MLE will version control models and monitor the performance. And as the newer models come in from the data scientist, pushed into the model registry, the old versions will be slowly staged out in A/B testing models. So let's briefly talk about data engineers and how the data pipelining should work. Again, very high level, I've covered all of this most of it, but I think this is first principle thinking, so we should understand, because this is actually the very first critical point, which is the data engineer, the data scientist, and SME will kind of partner together, and then they'll take something called long and tall tables, right? And then they'll create feature stores. So you're talking about transactional systems of hundreds of DBs that you have, and you're pivoting them, merging them, and just creating feature stores. The data scientists will actually do the same thing and create their own feature stores, or ask the data engineer to leverage the feature store for them, depending on their skill set. We'll talk about that in a bit. And as the newer data is coming in, the flow works that it goes into a transactional system most likely, and then automatically the pipeline will hold it and just transfer it to the feature store. And the data scientist models will actually just take that for training purposes and prediction purposes. The old version kind of looked like the bespoke ETL-like pipelines, which is the left side. So keep in mind, if you're talking about legacy operators, is that over 10, 20 years, companies have generated thousands, tens and thousands of tables. I'm personally actually I've kind of seen that personally, which is companies have tens and thousands of tables just lying around. And a data scientist, if they are querying these servers, two things is going to happen. One, when they want to iterate through the model 6 or 7 months later, that source of truth, they'll have to either do code review to make sure where these sources were, or they're going to actually, or the sources might have changed. Essentially, what you do is you move to the right side of the version, which is take all those sources, single sources of truth you have, and put it in one place. So even if the changes are happening, model 1, 2, 3, 4, 5 are always accessing the same feature store. So even though there's any modification, the pivots, long and tall to the side, even the schema changes will be dynamic. So now that was a little bit of a technical jargon. Now we're going to talk about from a PM standpoint. How do you go about selecting the project selection? There's 5 critical components to this. What is the expected level of usage by the end user? Meaning that, are you building a one-off solution for one user in the corporation, or is it going to be scalable? Are you going to take it yourself? Are multiple users going to be used? Not scalable, sorry. Then the second thing is, can we build it? We're going to talk about, this is where the architecture portion comes in. Do we have the architecture to build it? Does it have potential to get big, meaning scalability? Again, I'm giving you guys hints of the next 3 S's. So scalability is an issue. Can we scale this? Meaning that, let's just say we solved one problem. Let's just say we solved one problem for one stock exchange. The methodology and the architecture is going to be fundamentally sound. And so you can take that same approach 50% of the way and just clone it, and then take the other 50% for the modeling and the deployment aspect. But you have the architecture to scale the same solution. So the level of friction is reducing dramatically. Then you ask, have you standardized the architecture? So the question kind of comes in, okay, are people using, and I'm going to go this analogy over and over again, do you have, for example, Power BI and Tableau? Are you paying for 2 subscription for a tool that can fundamentally do about 90% of the same thing? Is that necessary? And I'll talk about why that's important. Then we have one-way door versus two-way door approach, and stole this from Amazon, which is basically they have this philosophy that if a person comes in and makes a pitch idea, that person is allowed to backtrack and pivot in data science or any product solution, in fact. Meaning that your first idea or your second idea might not be something that can work through, but you need to have a backtrack and back pivot, because during that EDA portion, when you're exploring the data, that problem statement might not be something that you want to solve for, but there might be 3 or 4 different other 10x factors that you can address. So you need that optionality. So that was from an MLOps project selection. Now we're getting into the meat of the bone, which is how do you actually go about standardizing your architecture, scaling it, and simplifying it? So from a standardization standpoint, what you're really thinking about is, do I have duplication of lots of tools and cloud technologies that are just clones of each other? They basically get you about the same thing, but you have duplication. Couple of reasons why, because if you have duplication, that means that the sophistication of the users is split, meaning that one user might be an expertise in one tool and the other one might be in the other tool. So now you're getting a split, and that kind of fragments into a tree, meaning more and more splits occur. So the complexity of your architecture is getting way too out of the, than it needs to be. Scalability, meaning that, are you able to take a containerized desktop model, let's just say, or a cloud model, and do you have all the stuff that is needed on hyperscalers to automate that pipeline? Everything from data pipelining to experimentation to deployment on an automated fashion. Do you have those features? So we're going to talk about how to do that. And then simplify. This is probably the most important out of the 3, is that a lot of times data scientists and ML engineers will try to build a very complex system and forget that in the end, the end user is not familiar with the complexity of backend and technical jargon. They need something very simple. So what we're going to show is a real world example of a very simple end user ingestion tool that we built that addresses 3 levels of your internal stakeholders. So we'll talk about that, which is the executive team, which is the managers and stakeholders, and the action item folks, which are the analysts. They're going to access the exact same tool, and they're going to be utilizing the same metrics that are provided in the same dashboard. So they're not going to different places and being at different pages when they're kind of having discussions. So why should I standardize? So let's just say that, somebody, and this is like I know I'm going to create controversy over this, but let's just say Python versus R, right? You have a team and somebody likes R, somebody likes Python or whatever. Totally fine. I know I'm going to get some pushback on the comments, but I'm going to say this anyways. So let's just say that, there's one person out of your team of 5 that knows R code, and the other ones are, let's just say, in Python. And then let's just say 5 years go by and there's 10 models that this person has built in R code. And then what happens is that person leaves. The other 4 people don't know how to read the R code. Can you do it? Yeah, absolutely. They can learn. They're all programmers. But is there a need to do so? Probably not. Now you might say that from an MLOps standpoint, the R code and the documentation will actually prove it, but you still have that level of friction. Minimize that, because that is your single point of failure. If you build models that are 10x models and there's tens of millions of dollars in line, which I'm personally I've kind of dealt with, is that if that person leaves, you are literally, and the model starts drifting, God forbid, you are at the whim of actually trying to figure out what that code is doing. So I'm just giving you an example. I know I'm going to get pushback in comments. Can't wait for that. And then the other part is you want to invent new ideas, not new rules, meaning that the more tools you add to your stack, the more rules you're going to have to build. So for example, authorization, cybersecurity, privileges, tokenization, all that stuff, just more and more duplication. No need for that. Keep it simple. So how do I standardize this? This was the problem that we kind of came through, was that, oh my God, there's just so many things out there that we have to look into. So the idea that we kind of came up with was an approach, which is we call the MLOps orchestration tool selection process. It depends on 4 factors. The skills of your team, meaning that you have your data engineers, you have your ML engineers, and you have your data scientists, obviously. Their skill levels and their needs for what tools they want to use, and the data that you're kind of, think about the 3 V's now, and the volume, the veracity that's coming in, you have to address those when you're talking about which tool you want to select. If folks are not well-versed in distributed computer, do you want to upskill them, or do you want to get a third-party tool that just handles that for you? Your budget, again, that's, it's pretty simple. The third one kind of gets very interesting because you're talking about automate part of your pipeline or the entire pipeline. So this really is an age-old question that any company for everything has to answer: buy or build. That's where it kind of gets tricky. Do I want to build an internal solution, or do I want to just buy the solution? One has a cost, the other one has complexity. I mean, the other one has cost too as well. So people do in hybrid stuff. So for example, we can actually just do data engineers who are very, very good with SQL and data warehousing capability. And in that case, you just use a tool that allows you to take it to the next level, which is hyperscalability. So in this case, Snowflake. And then the last one is ease of integrating the new tool. So if you get like a SaaS product and it doesn't allow other open source capability to kind of interact or pull data from it or use the services, now you're in a siloed containerized environment again, and you can't even do anything inside that environment. So be very careful when you kind of get into those systems. So essentially, now I'm going to walk you through our approach of, how to kind of come up with our use case. So what we were looking for is like, distributed computing. We are looking for the ability to have feature stores, everything from model deployment, model evaluation, and then obviously probably the one thing that wasn't covered by most was the data warehousing on hyperscalability. So on every single category, you'll see that there's a fundamental gap that's being filled by one tool alone, which is Databricks, obviously. So it allows you to do a lot of the AI lifecycle, not the data side, just the AI lifecycle. So how do you fill the data side? Well, the data side is, if you have an in-house team of like people who are expertise in data warehousing, SQL and stuff like that, but you need hyperscalability, you find a tool that will match that condition, which is Snowflake. So I'm not gonna get too much into it, but what is Databricks and Snowflake? I think we all know, but the founders come from a very technical background. One comes from distributed computing and one comes from DBs. Now, this is really how you address that architecture question, which is you have the AI side, you have the data side, and then in the middle, you have the hyperscalability side, which is your Microsoft Azure, AWS, Google Cloud. The Databricks side will do like a lot of the AI stuff. It can do a lot of the data stuff too, but I'm just moving towards that side. And then the Snowflake side will be, hey, data engineers don't have to learn a lot of new tools because they are very good. They understand data modeling. They understand star and Snowflake schemas. They understand all that stuff, fact tables. So from a data modeling perspective, from a schema standpoint, from a language perspective, from a hypercompute capacity, Snowflake answers that question on the data side. And on the ML side, Databricks is the leader, in my opinion. And then in the middle, for the data pipelining and orchestrating your entire pipelines, AWS, Google Cloud, and Azure, they all do the job. Again, you don't want to, this is where I kind of was saying, you don't want to have AWS and Google Cloud subscriptions at the same time. However, it's a possibility. You can totally do that because AWS might have services that Google Cloud doesn't. If you have that edge case, go for it. But from my experience, one of them will always suffice. I know there's hardcore AWS versus Azure guys, so I'm going to hear some comments on that too. So this is the architecture. Databricks for machine learning, Snowflake for everything else. Now you'll notice that there's something on there that I haven't talked about at all, which is Atacama, which is a data catalog. I'm going to walk you through exactly what it looks like in an actual use case. So at Atacama, what you're seeing is the data is queried. The data scientists, the SMEs will interact with that, move into the data warehouse, and then in the data with the Snowflake data warehouse, the Databricks will pull the data from Snowflake to do ETL, or the Snowflake can do the ETL as well, and then the machine learning algorithms will run. You'll see that I've kind of canceled out the cross down there because the Databricks was outputting and interacting with the Power BI dashboard. You don't want that. from my standpoint, so what I did was, push all the model outputs back into Snowflake, because again, the motto is Databricks for machine learning, Snowflake for everything else. Take that Snowflake output and connect it to Power BI. Now you have completely compartmentalized specific use cases for these tools, and it's standardized. So one of the most challenging parts about data is, I was kind of alluding to it, is that legacy operators have tens and thousands, but even like 50, 60,000 tables generated over 10 or 20 years. When a data scientist comes in, you have absolutely no idea what data the company has and even where it is or who to even begin talking. So in this case, a catalog comes in very, very handy. A catalog knows exactly precisely where all the data in the company is, and it's been attached to a key term. So in this case, what you would do, the top left corner is search for the term. So let's just say in here, like I'll just say a stock ticker symbol. And then you just look for all the records anywhere, all the tables that have a reference to that. So in this case, every row is a table. And you can see that the very first row has about 399 million records, rows of data with 11 attributes. And probably the most important feature is the location, which you can see on the right side, which is precisely where in the organization this table is located. So again, standardization and simplicity keeps it very simple. The data scientist doesn't have to spend 3 months, 2 months trying to figure out. And then obviously there's a bias of the domain expert who might just know that there's these 10 tables, when in fact the company might have 100 tables referring to that same thing that you're trying to solve for. One of the cool features is that, again, the data catalogs updates itself, so you actually understand, okay, how many null values there are. So you don't even have to do the statistical, the very, very bare minimum statistical analysis of your data tables. The model the catalog handles that for you. There's a lot more functionality, but in the interest of time, I can't get into it. High-level primer, again, Databricks allows you all this. So it's well catered for all things ML. So you can do experimentation, you can register your models, you can deploy it. Databricks also offers feature stores now and ML flow, which will actually allow you to do experimentation, deployment, staging, all that stuff. The key thing is, if you're dealing with hundreds of sources, which is like, let's just say you have third-party vendor APIs that you're scraping data from the web from, you have in-house on-prem data sets, and then you're moving a lot of the data around, you want to have a feature store because it'll standardize that architecture. I can't emphasize this enough. Have a feature store. And again, high level, this is kind of how the models work, is that the load data goes into training models, the ML runtime spins up, the ML flow, it runs the experimentation, you load the models back into a model registry, runs a predict function, and then you log the predictions. The cool thing about this entire architecture is the middle one, which is the monitor drift. Inside the monitoring drift, you have the data drift, which I talked about, target drift that we talked about, and then obviously the model drift itself. So you want to kind of monitor all those things, the performance analytics. This is kind of how you use it. And right in the smack in the middle is the feature storage, how the data is kind of interacting for the models. Again, very briefly, bronze table is a long and tall table that a data engineer will create. A silver table is more like a filter augmented version, meaning that it's a feature store. That's where the feature store will reside. And then the outputs will actually be put into a gold table, which will be used for Power BI analytics. Backend, this is kind of how it works. The Databricks and the Snowflake kind of interact and talk to each other. I'm not getting into all the technicals, but essentially what this allows you is that if you have data residing inside the Snowflake environment, you can write a Databricks using this connector, spin up your compute capability, or and we're going to go through a use case, and then pull all that data into Databricks environment to run your machine learning, and then push it back out to Snowflake, just like I said, using these connectors. They make it very simple once you figure it out. So I want to show you something from a SQL runtime, like what is this hyperscalability that we're talking about? So these are the actual use cases. So what you're looking at on the right side, we just queried about 453 million rows of data in about 5 minutes. And the second row, which you'll look at, is that, again, 453.2 million, but in 1 minute. And you can see the byte scan. The byte scan is actually a compression format that Snowflake looks at, but it's a lot more than that. And the reason why those two exact same queries ran at different times is because I just changed with one click the data warehousing that we were using. So you went from a small version to a medium version, for example. So that allows, based on the query complexity of your query, if you have low latency models that need to be run right away, you just adjust for that accordingly. So you basically reduced your runtime by about 450% over there. And that's kind of how it's really working, is that, okay, I want simplicity, but I want scalability. How do I merge those two? This is exactly how. Another way you can look at it is that in the bottom, what is very interesting is that 149.9 million rows of data in 4 minutes, not very impressive. But what's very interesting is that all these queries ran in parallel together. So the same data warehouse ran them. So they started at the same time and they all ended at the same time. Now you're talking about, how did that data warehouse do 149 times 7? So that's how much data it churned through and then just provided the data for you. Another example is, okay, now that was a task manager, right? Like I'm creating tasks for, let's just say optimization. So not optimization, we were creating new tables, for example. Let's just say that. In this case, I'm running just my database queries. So in this case, what I can do is about 500,000 rows of data in about 4 seconds, right? I can optimize that even further, and I can download that in any format, or I can push it out to a data lake or a Delta lake. Now we talked about Snowflake. Now let's just talk about the machine learning side. And now it's going to get very, very juicy for the ML folks. The data warehouse has all this data that's come in, and we've created all these tasks, and we have all this big compute. But now I want to do some ML stuff on it. How does that work? So what you're looking at is actually, and I'll show you the runtimes right in the next slide, but essentially what's happening is the very first notebook is pulling the data from the Snowflake side. So now you're using distributed computing to pull data into the Databricks environment to run ML. And then each notebook right here, the first one and the second one and the third one are actually separate ML models that are running. So you can even have like up to 10, I've done up to 10 or 15 different ML models running from that single source of truth for experimentation purposes. And then they're pushing it out. And what is not kind of clearly shown here is then the model outputs are pushed back into the Snowflake for output, for dashboarding. This is kind of how it looks like. So keep in mind that, you have 3 over here. So we have 144 CPUs, which is 144, 144, 144. And then each cluster has about 1 terabyte of RAM, because that's what we needed for our algorithms. And in the bottom left, you'll see the utilization, which is that the seed cluster CPU usage is about 88%. So from the 144 CPUs, this is how much is being used. And as time goes by, the memory uses the 1 terabyte, which actually is kind of scaling up. And just to push it to the next level, in this case, you're looking at, again, 112. And in this case, it was 10 notebooks. So you have 112 times 10. So there's 1,120 CPUs running. And the utilization for the last hour for that cluster was 100%. And each one of them has about 650 gigabytes of RAM free right now. Total is 808. And then obviously the cluster CPU last hour is about 90%. So now you're taking all that data from Snowflake, pulling it in and running it on distributed computing on so much power. And that is where the scalability is coming in, but the Databricks side is handling the complexity of managing those things. So we talked about all that stuff now, the Databricks, the Snowflake, the data catalog. Now let's talk about the very, very last part, which is probably simplicity. There's 3 levels of end users: an executive team, management stakeholders, and analysts. And out of these 3, you have to be able to provide a very simplistic, all that complexity that I just showed you. No, they don't need to know that, and they're not interested in that, to be frankly. What we want to show them is the value generation. What did you do out of all these things that you just used? And you want to do it in a way that they're all using the same tool. And the same tool is something like this. So essentially the same dashboard, you're going to see level 1, level 2, level 3. It's all the same dashboard. And the executives are coming in here. And in this case, for example, the SVP of engineering, the SVP of engineering, in this case, wishes to know how many assets on all the different sites, for example, have had anomalies according to the machine learning models we are running for the 2nd week of December 2021. And this is the only thing that they care about is like, okay, one asset had 94 anomalies, the other one had 87, 83. And there's a different metric that I can't share, obviously, that there is a dollar value attached to it. So this is the executive purview. Now you move to the next one, which is level 2, manages stakeholders. So keep in mind, they use the same dashboard, they do a drill down feature, and they go into it. Now the managers and the stakeholders are trying to analyze, okay, now we know what the anomalies were, but now let's exactly look at which anomalies we need to action. So from the analytics perspective, again, the same dashboard, there is 1 billion rows every day generated on this exact same dashboard in the backend. And it has low latency. So they're just looking at the outputs within 1 second response. So in this case, what they can do is, remember when I was running the machine learning models, there were 3 or 4 models that were running in parallel. There's 10, 20. Those are all different models meaning that the target right here is that. So there's 10 or 20 different models with different optimization target outputs that can be seen in the same dashboard. So you don't have to create 10 or 20 dashboards. You create the same one and they just filter for that. And in the back end, the complexity and the scalability is just being handled by the Snowflake engine because your Power BI is attached to that. And then obviously, the feature part, we'll get to the next part because the analyst is going to look at. But this is what they're looking at and saying, okay, which ones do we want to take an action on? The third one, again, it's exactly the same dashboard. You're drilling just down into it. So nothing is changing. They're not going to a different web page. It's all in the same dashboard. They go down. Now the analyst needs to create some action item. So they go and they filter in the previous slide, the target, and look at the features. And they go down and they say, okay, this is what happened. And this is precisely when it started deviating. So the analyst only cares about certain parameters. They don't care about, the business KPIs per se, because they need to get this asset fixed and back up online, or fail it. Even more importantly, let it save it from failing, because that's lost revenue. Another view would be like exactly the same thing. You go, again, exactly the same dashboard, just filtering with the target and feature and looking at completely two different models in the same dashboard. The key term here is simplicity. So the key features of dashboards is you have to have a sub 3-second response time. 80% of the core needs are met by default settings. The very first thing that they look at needs 80% of all the things that they should care about. And after that, you can start kind of drilling down and playing around with it. Again, the model is not flashy. We have flashy dashboards from a business KPI perspective. From an MLOps perspective, you don't want to keep things flashy. You want to keep it as simple as it gets, so that if the managers, the stakeholders, and lastly, the end users, they're sitting in a room, they are looking at the exact same point of view, and they are very comfortable using the tool. And that's where the buying really happens, because they're not flipping around on different tax boards. And then level 2 and 3 are not defaults. This means that the level 2 that we just looked at and level 3 that we just looked at, they're not defaults, meaning that that's not the first thing an executive team member sees. The very first thing is your first primary target, and then you just drill down and drill down. As people get more sophisticated and drill down, they can actually use the features of that. So towards the end of our slide, of our presentation, the key point to make here is that simplicity is that it takes care of everything. So standardization, your architecture, how do you reduce that friction? So you walk through that process of how to select the right tools, the 4 criteria. The address the scale portion, which is, can we take containerized models, push it up, automate the entire data pipeline and the ML pipeline. And then obviously, lastly, we saw keep things simple for end users, meaning that know your audience and always cater to them. That's the end of my slide.
All right. Thank you, Wish. So anyone who has any questions, please feel free to type. I'll be showing them up on screen. And I guess we can start off with Ben's question.
Of course. First question on pushback. Take statistical models which are implemented in R packages, but not Python equivalents exist. Very good point. Very good point. Again, in that case, you wrap it around, but you have to have a business use case. So what I would do in that situation is say, this wrapper functionality that you're talking about, the edge cases, the packages don't exist. If the Python team cannot create those equivalents, which is actually quite plausible, then you move to that one case, edge case scenario, and say, in this use case, we're going to take that R code and productionize it, because it just doesn't make sense to build custom packages that are already implemented in R. So that's an edge case. Totally game for it.
Doesn't look like we have too many questions. I have one for you. So if we're wanting to start this whole process, where should we begin? Like, you say you want to simplify is the main goal, but what should we start by simplifying?
Know your target audience. So know what they're trying to solve and know your data. Those are the two critical components that you have to absolutely understand to its core. And that is a good starting point, because if you have the data and you don't have the architecture, then you need to be able to build that architecture for the next step, which is a data scientist coming in and utilizing that. Oh, there's a question. Do you think as a data scientist, it is necessary to learn about coding in data warehouses such as AWS, Azure, or Google? So I think what you mean is like data warehouses such as like, Snowflake or SQL servers. I would definitely say yes. I think the very first tool that you should learn after Python or R is SQL. It is absolutely paramount, because if you cannot pull that data and you're relying on another party to pull that data in, you're going to actually, the latency issue of how much time it takes before you can get to the next level is going to struggle. So a data scientist that is well versed in Python and SQL, or Python R and SQL, is going to be very well positioned to generate value for the company. Either I did a great job or I just really confused everybody. So I'm hoping it's the first one.
Yeah, so I think, okay, there is one more question.
Oh, there you go, Michael there. Oh, TransAlta folks. How has the cost grown and been managed with each additional models and the data to build it? Are they running and score live, or were those dashboards showing a previously stored result? Good question, man. That's a great question. So regarding the costs, we treat every, I'm not talking about Capital Power, actually. I'm just talking generally when I do all these projects. The cost management aspect is treated from an R&D perspective, meaning that depending on the scope and the high visibility and the ROI, meaning that the expected ROI. So for example, if you're doing just, low-level hanging fruit, and there's not a lot of 10x factor in that, the cost will be a portion of that. But if we're doing like a 10x R&D activity, which is 6 months, there's a bigger budget for that because it's a bigger appetite. You score that home run, the ROI on that is going to be 10x, so you're going to recuperate your cost pretty quickly. There was another question in there. Are they running and scored live, or what the stores? No, they're running and scored live dashboards. They're not storing any previously stored result. It's like the moment that my models run, immediately right after that, the results are pushed out to the dashboard. Oh, there's another. Between AWS, Azure, or Google, which cloud system do you think is the best? I can't answer that question. I wish I could, but I'm an Azure guy, but I'm also learning AWS right now. So I like them both. I'm not familiar with GCP, so I don't want to make stuff up over there. Over the past 12 months, how has the literacy of MLOps developed at Capital Power and the YYC marketing general in opinion? So I can't speak to Capital Power because I do work at Capital Power, but I'm not here as a Capital Power employee. But what I can tell you in the general scope of things is that the literacy of MLOps has, I would say, year over year from last year has gotten, dramatically improved, because I think more and more companies are going through digital transformation. They have analytics capabilities, and now they're saying, okay, we have this, but we want to scale it. We want to get some returns on this. And I think they're getting more and more experienced with the returns only come through MLOps. Data science is about 20-30% of the way. But if you want to scale it, productionize it, automate it so that the data scientists, data engineers can do something else from a value add proposition standpoint, you are actually looking at that. So the sophistication level has dramatically improved, I would say. When talking about 1K CPUs and terabyte scale memory, what suggestions do you have to keep that manageable? Very good question. So depending on which system you're using, if you're using a Spark distributed computing system, I would say definitely learn how to optimize your queries and how to use Delta Lake, which is like, it allows you, because there's something called optimize function. You can optimize your tables, and then the queries run quite faster. The other thing is minimize wrapper coding, meaning that don't put too many layers of wrapper methods inside your languages. So if you're going to stick with Spark, don't put Python code inside that Spark. It's going to slow it down dramatically. And from a cost standpoint, what I have found is experimentation is key here, because what you do is you give it as a computer scientist, we are trained to think about worst case scenarios. So in my case, I always think about, okay, what is the worst case? How much data could really push the system to the edge where costs will go up? And then there's actually a Spark, a calculator for kind of optimizing your query runtime versus the cost. So what you can do is experimentation. You try to optimize for different clusters. So you pick different worker sizes, you pick different driver sizes if you're pulling a lot of data into the driver, and then you just kind of optimize that. And for trial and error, you will figure it out. And then the most critical part is, which I think people is to look at the logs, because in the logs you will see how the JVM is interacting and putting the outputs in there, and it'll make it very clear exactly which line of code is causing complexity into your issue. So you optimize from that. But from a cost standpoint, just changing the number of workers by a certain amount will optimize it, but you need to know exactly how to do that. So that's quite technical. Lots of models get created and thrown away. Do you have any suggestions on how to minimize the efforts? Oh, that is a billion-dollar question. I would say look at the data and see how. Okay, so here's a good example. Hypothetical case is that from a P&L standpoint, there are certain problems that you only need to do 51% better than the competitor. Then the other ones are actually you need to have 99% accuracy, right? So depending on that case, you want to see, okay, if the 51%, if that's what the business use case is, high success rate is highly improbable. So if you have the other 99% use case, tackle those first, and then go to the ones that are like the super edge cases, the 10x factors. The way I manage my portfolio is that I have an asset management portfolio, for example, and then I have an algorithmic, from a trading, like a stock trading portfolio perspective. And the third one is the R&D. The R&D one is like a 10x factor, the baseball, hit it out the home run, and then use that. That one, I'm not going to utilize right away. I'm going to try to solve the other ones before I go into the R&D activity. If we can save the data in Azure, Google, or Azure, then why should we use Snowflake? Great question. It is all about utilization. So again, I talked about DBAs or people who are SQL experts, for example. 100% you can go there, except that Snowflake provides cloud storage, right? Data lakes, data and Delta lakes are completely different that are within the Azure environment. Now, to utilize that data, you have to spin up some sort of an endpoint to start querying that data. And that means that there's added cost to it, meaning that if you are running an Azure ML service, you're spinning up these clusters for no reason. In Snowflake, it's literally pay as you go. So meaning that you run that query, that stuff that I showed you, there's no spinning up. It's there, and it is available in 1 millisecond. So you're running a very complex SQL query, and then you just execute it, and it's done. And the storage is there, and the compute's there, and it's all in the same place. Whereas with the other case, you have the storage, you're completely right, but you don't have the compute. You have to get the compute somewhere. I would agree. The Cloud Console is hostile. What tools are you using to schedule or orchestrate data pipeline? Azure Data Factory, and in AWS, you also have Glue ETL jobs. You can do either or. ADF provides less functionality, but it's more robust because it limits you to kind of functionality you can use. AWS Glue has even a catalog built into it, so you can use your ETL and ELT using Spark connectors or whatever you want, and it's more robust and sophisticated. So if you're more technically inclined and you need more functionality, go with AWS Glue. Can feature stores be considered as knowledgeable by SME, domain, or purely data-driven? Yeah, you know what? That's true. I think it's purely data-driven. That's a good question. I wouldn't say that it's a knowledge base for SMEs, because the knowledge base for SMEs would be their data catalog and then querying the SQL, because then the feature stores are really just for data science purposes, because you're doing so many experimentations and creating so many feature stores to see which features kind of make sure that your model does really well. It's purely from a DS standpoint, it's an ML standpoint. I wouldn't say it's a knowledge base for SMEs. They shouldn't be interacting with the domain experts. Will need technical expert capability to actually interact with feature stores. As a newcomer to this, I was wondering what is available to us for free that I could use to get acquainted with things like MLflow pipelines. You know what? That's a valid point. I would say that MLflow is open source, so you can use that and learn that right away. Databricks makes it. So what I would do is take Databricks. They give you about $250 in credit, and MLflow is completely integrated into that. So it's open source too. So if you're doing something in a Jupyter notebook, you can actually utilize MLflow as well. Now there's a little bit of complexity to it. Across the industry, Python and R obviously both leaders. Do you think ML.NET is a viable language in the industry, or Python are the de facto standards? I would actually just throw that back and say, well, Julia is actually a pretty good contender too. So there's lots of optionality that's coming in. I would just say that Python and R are probably going to be the leaders for a very long haul. And I would say I lean a little bit towards, from an MLOps standpoint, I would lean even more towards Python, because a lot of the ML engineers and computer scientists, they're trained in Python-like languages when they're in school from an education. Ours is a little bit different. So it's kind of like, from an MLOps standpoint, I would say even Python is a little bit of a leader. I know I get pushback from this, but pure from a data science, they're net completely equal. But from an MLOps standpoint, it's easier for software engineers to kind of like, read Python code versus R code, from personal experience. I might be wrong, but just from what I've seen, they like Python code because it looks a lot simpler than what they're used to. What are some of the common tripping points that people already make when building an ML set on huge data sets? Yeah, wow. You guys are asking very, very intelligent and challenging questions. I would say probably the biggest tripping point is when the subject matter expert and the domain expert try to bias the directionality of where the model should go. So the input parameters are X, Y, Z. And I'll give you an example. So for example, legacy domain experts who have been doing something for 10 to 20 years, they have done polynomial regression in Excel spreadsheets, for example. When you move into like ML stuff, they might try to solve like time series problems, and they might say, well, why don't you just take the daily data and then like, upsample it and put it into hourly and merge all these hourly data sets together. Well, then you have to kind of explain to them that, you're making a lot of assumptions, especially if you're dealing with something like weather data, for example. So controlling that conversation, as in, hey, you're the domain expert, teach me everything that I can in a limited amount of time about what you do and what I can do for you, right, for a living. And then let me be alone and let me just solve this problem for you. So personally, I would say that is a thing when everybody wants to have feedback. The approach that I take is, for the first 2 or 3 months, I'll sit down and I'll just learn through osmosis. So sit down, don't give any opinions about their industry because they're the experts. And then the time comes for me, I expect the relationship to reciprocate. So that's kind of where it gets very challenging. Regarding standardization, do you recommend picking one language or becoming experts in both? Pick one language and stick to it. Again, standardization, just pick one. And I have a preference, Python. Obviously, I've kind of made it clear. Ben's not too happy about that, but I love Python. I'm going to stick with that, but you don't need to learn both. But you know what? Here's an edge case that you can kind of utilize. If there are people in your organization that are hardcore from using statistical modeling using R, then it probably makes sense, even if you have Python, that you learn R, because that's the environment that they're going to be comfortable helping you out if you get struggle with productionization or development of models. As a hardcore Azure user, have you tried Azure Synapse along with Databricks? Yep, I have. I actually tried it multiple times. I don't think Azure Synapse even closely comes to Databricks. Their features, functionality, I hope there's no Azure reps over here, but their functionality and the features are not quite there. Databricks is just far, far ahead from what Azure Synapse has to offer.